In this video, we're going to have a look at storing energy in a capacitor. So you might remember that our capacitor is basically two parallel metal plates which will be charged up. Each plate will have an opposite charge, producing a potential difference across it. Now, the energy stored in a capacitor is stored as electrical potential energy, and it's forced onto the plates by the battery. Over time, as we saw in the last video, the potential difference across the plates is going to increase proportionally with the charge stored. But of course, as we're adding charge to that plate, it's going to become more difficult to add more charge. If I've got a build-up of negative charge on this plate here and I'm trying to add extra electrons to that, the repulsive force between the plate here and my electron I'm trying to add on is going to go up, and that has consequences to the energy provided by the battery compared to the energy stored by my capacitor. So if you imagine that I want to increase the charge that I've got on this plate here by a very small amount of charge, so that you then have original charge plus new charge. The battery has to do work against the repulsive force of the plate to get the charge onto it. And that energy is going to be equal to the potential difference times the small change in charge. Now, if we take that idea forward, we can now consider what we'd have to do for every single step from PD equals 0 over the capacitor to the final charged potential difference. And if I were to draw a graph of this, we'd find that the total energy stored is found by adding up the energy stored in each small step. So for that small little change I made of Q to Q plus Q, this here in green would be the energy stored for that change in charge. For the energy stored in the change in charge and therefore the change in voltage, in potential, across my capacitor, I need to take the entire area underneath my graph of voltage against charge. And so the easiest way to work that out is to take my Q, times it by my V to get what this whole rectangle here would be, and because I'm only looking for the area under the graph, I halve it. So the energy that's stored in a capacitor is equal to the area under a potential difference against charge graph. And from that I get my energy equation. E equals a half VQ, or a half QV. Depends on how you'd rather remember it. But because Q is equal to CV and V is equal to Q over C, we can actually rearrange those equations. So because this is a revision video, we're not going to go through the derivations, but you do need to know that not only is E equal to a half times the charge times the potential difference, but it's also equal to a half times the capacitance of your capacitor times the potential difference across it squared, and also equal to the charge on the capacitor squared divided by 2 times the capacitance, or a half Q squared over C. Now, all of these equations can be called upon, and many of them can be used in the same situation, as we'll see with one of the examples later on. So, if I wanted to calculate the charge and the energy stored in a 10 microfarad capacitor, which has been charged to a PD of 3 volts, what I would need to do is remember my 3 potential equations to use for finding the energy, and look at what I've got. I have a capacitance, and I have a potential difference, so I have a C and a V. So my preferred equation is going to be this middle equation here. E equals a half CV squared. When I plug my numbers in that I've got above, I get an energy stored as 4.5 times 10 to the minus 5 joules. What happens if I up the voltage and the potential difference across the capacitor to 6 volts? I'll use the same equation. plug my numbers in, but because I'm squaring the voltage, doubling the voltage actually quadruples the energy in my capacitor. So doubling the voltage quadruples the energy. Let's have a look at another example. If a 60,000 microfarad capacitor is charged from a 9-volt battery, it's discharged through a bulb in a flash that lasts 0.2 seconds. First thing we want to calculate here is the charge and the energy stored in the capacitor before it is allowed to discharge. Well, for the charge, and let's not forget our energy equations, I can use Q equals CV, rearrange my capacitor equation, plug my numbers in, C, 60,000 microfarads, V is my 9 volts, and I get a charge of 0.54 coulombs. How do I work out the energy stored in the capacitor? Well, let's see what we have. We have a Q, a charge. We have a capacitance, C. And we have a voltage, V. So I can use E equals a half QV. And when I plug the numbers in, I get 2.43 joules. But I could also use E equals a half CV squared. And when I plug those numbers in, surprise, surprise, I get the same value. So the key to these questions is look at your capacitor energy equations, see what bits you have to pick the one that you're going to use. Now to work out the average power to the light bulb, this is where we have to go to another of our electricity equations, and remember that the power is equal to the energy divided by time. Now I have an energy here, my 2.43 joules, and I have a time of 0.2 seconds. So when I plug that in, I get a power of 12.15 watts. Final example is this one here. I have an uncharged 1.5 microfarad capacitor and it's connected to a 3-volt battery. What is the charge and the energy stored in the capacitor going to be? Well, I can go back to using Q equals CV for the charge, plug my numbers in from above. Here I've got my capacitance, here I've got my voltage, and I get an answer of 4.5 times 10 to the minus 6 coulombs. How do I work out the energy stored in the capacitor? Well, I have a charge, I have a voltage, and I have a capacitance. So again, I could use any of the equations, but I'm going to go here for E equals a half CV squared. And plugging my numbers in, I get 6.75 times 10 to the minus 6 joules. So how do we work out what the charge and the energy supplied by the battery would be? Well, the energy supplied by the battery is going to be twice the energy that is stored in the capacitor. If you think back to the graph, the energy stored in the capacitor is the area underneath that, which is a half of our Q times V. Now Q times V from the battery gives us the energy supplied by the battery. And therefore, if we double the energy stored in the capacitor, we get the actual energy that was given to the system by the battery in order to charge it in the first place. What's happened to that other 50%? Well, it's been lost as a result of having to do work against those repulsive forces. There have been heating effects inside, energy's been lost to the system, and so you only get half of the energy that you supply to the capacitor actually stored.